Hello, again, this is Ismail Badran, Assistant Professor of Physical Chemistry at Qatar University. And today we are going to continue with Chapter 4, Chemical Equilibrium. So in the previous lecture, we talked about the definition of the pH and its relationship with the concentration of H plus and OH minus. We also learned how to calculate the pH in solutions. And also in the previous chapter, we talked about the definitions of weak acids and strong acids based on the Bronsted-Lowry theory. And today we are going to continue with this, and we are going to learn how to calculate the pH of weak acids. And also we're going to talk about buffers and their importance in daily life. So let us start our discussion with asking this question: what are the major species that exist in aqueous solutions of HNO3? So as you know, HNO3 is nitric acid and it's a strong acid. It's one of the strongest acids in nature. Now, if you throw some HNO3 into water, HNO3 dissociates completely into its ions, the nitrate ion NO3 minus and H plus. So if you actually look at this in the solution here, if you imagine you can have a microscope and you look at the solution, you will have no HNO3 at all. You will have that it's only going to be NO3 minus, the nitrate, and H plus. And the amount of HNO3 solution, it's almost non-existing. Now, the story will be different if you just change that into HNO2. Nitrous acid, HNO2, is a weak acid, and therefore, when you put it in water, it's going to dissociate into NO2 minus and H plus. But the thing is, it's a partial ionization. So when you put this in water, HNO2, you will produce it NO2 minus, H plus, but you'll have a lot also of HNO2. So if you represent this in the graph here, you will be surprised that the amount of NO2 minus and H plus is very small, and there will be a lot of NO2, and that always depend on the Ka of the acid. So for weak acids, the amount of products is less than reactants in this case, and you will have a small value of the equilibrium constant or the acid equilibrium constant. So keep this in mind for the future slides here. We are going to use this to solve questions that are related to weak acids, and as it's also important to understand how buffers work. So how to calculate the pH of a weak acid? So as I said, the calculations of the pH of the weak acid is not straightforward. So for strong acid, it's easy. For example, if you have a 0.1 molar HCl, so the HCl will completely dissociate into H plus and Cl minus, and therefore the concentration of the H plus in the solution is equal to the initial concentration of the HCl. In that case, it's 0.1 molar. So if you do the pH for that, and I think we have done it last time, you will find the pH is equal to 1. 0.1 molar of a weak acid, let's say acetic acid, the pH of that will be a little bit more complicated than that, and we're going to show you how to do that, and you will find that the pH of a weak acid for the same concentration will be way different than a strong acid. Let's start with an example of calculating the pH of a weak acid, which is the acetic acid. Acetic acid lends a sour taste of vinegar and is produced by aerobic oxidation of ethanol by bacteria in fermented beverages. So usually we prepare acetic acid from ethanol. And this question says, estimate the pH of 0.15 molar CH3COH, which is acetic acid, and also 1.5 times 10 to the minus 4 molar acetic acid. Okay, so example 4.5 is asking about calculating the pH of acetic acid. So acetic acid, as I said, it's a weak acid. So when you put it in water, it's going to form your H plus, H3O plus, the hydrogen ion, plus CH3CO minus, which is the base, which is the conjugate base of that. And this reaction, the CH3COH is acetic acid, it's the acid. And H2O liquid here behaves like a base, because as you know, H2O is amphoteric, and that means it behaves like acids and bases. So it behaves sometimes like an acid and some other times like a base. In this specific example, it behaves like a base because it is donating it's accepting the H plus from the acetic acid, and CH3COH is the proton donor here, and H2O is the proton acceptor. So we can simplify this question just for saving you time here by referring to the acetic acid as HA, and just removing the liquid from the equilibrium because it does not contribute to the equilibrium constant, as you know. And H3O plus, the hydrogen ion, I will just name it H plus, and for that acetate ion, we're going to call it A minus. So this is an equilibrium. That means if you have some kind of initial concentration for HA, let's say 0.11 molar, that's not going to produce you 0.1 molar H plus, as I explained in the slide before this. If you are going to solve a pH problem for a weak acid, you need an ice table. Ice table means initial concentration and change. So the concentration here that we're working with is 0.15 molar. So I have 0.15 molar of this. The Ka for acetic acid, it should be provided to you. It's 1.8 times 10 to the minus 5. Of course, it's unitless because the equilibrium constant has no units. So we'll proceed as follows. We start with this equation. The HA gives H plus and A minus. So you have HA, and you have H plus, and you have A minus. So initially, I means initial. Before doing anything, you have 0.145 molar of HA. You are having no H plus or A minus. And the change, so this is initial. And the change, you don't know how much this change is, so you can just refer this by X. So when the action goes on, you are losing some of the HA, so we don't know how much we are losing, so we just represent this by minus X. And we are going to produce some H plus. So because this is 1-to-1 reaction, that means it's 1 mole to 1 mole, then we have plus X here. And because the A minus has the same stoichiometric value as the H plus, that's going to be also plus X. So this is the equilibrium, sorry, the C, the change. Now at equilibrium, which is E, so that's why the ICE, you just add the I and C. So E is equal I plus C. So this is 0.15 minus X, 0 plus X is X, and 0 plus X is X. So this is your ICE table here that you're going to use to solve these problems. Okay, so from the equilibrium line, you can write down your dissociation constant, which is equal to the concentrations or activities of products divided by activities of reactants. In this case, the activity is equal to the concentration because of the fact that these are all in aqueous solution. So Ka in this case is equal to the concentration of H plus at equilibrium, which is X, times the concentration of the A minus, which is again X, divided by 0.15 minus X. Now we know the value of the Ka, which is 1.8 times 10 to the minus 5. That's equal X squared divided by 0.1 minus X. Now this equation, if you solve it out, you're going to get into a quadratic equation that might be a little bit difficult to solve. But here we're going to do some approximation. So here you can neglect X. You can neglect the value of X if you have an initial concentration, the initial concentration, okay, of the acid or the base over its Ka. If this is equal, if this is bigger than 400, So that's your rule here. Okay. If this value is bigger than 400, then we should be fine. Let's test that. So we're going to have to do a test here, just a quick test to see if we are going to neglect X. So the test is that the initial concentration is 0.15 and the Ka is 1.8 times 10 to the minus 5. Now, if you do the math here, you will get an answer that way more than 400. It's almost 8,000 something. So that's a big number. So this is bigger than 400, so we're fine. Then in this case, we can neglect X. By neglecting X, so the X squared in the equation will stay as X squared, and the 0.1 minus X is almost 0.1. So neglecting X does not mean that you delete X. It's just, you know, that the 0.1 is much bigger than X, and therefore the 0.1 minus X, it's almost equal to 0.1. So that's what neglecting X means. It's that the 0.1 is much bigger than X itself, and that's equal to 0.1. Okay, so we continue then. Then we said that 1.8 times 10 to the minus 5 is equal X squared divided by 0.1. So now that's easy to solve. If you cross multiply, you will get that X squared is equal to 1.8 times 10 to the minus 4. So X is equal to the square root of that number. And that will give you an X value equals to 1.64 times 10 to the minus 3. So 1.64 times 10 to the minus 3. Now what does that X value represent? If you go back to the question, X is actually equal to the X is equal to the concentration of H plus, as you see, at equilibrium. So that's the whole thing about why we are calculating X. So X is equal to the concentration of H plus after we put the CH3COH. So the question is asking for the pH. So the pH is equal to the minus log H plus, and that means it's equal to minus log this number, which is 1.64 times 10 to the minus 4, and that will give you a pH equals to 2.8. Okay, so this is how you solve these questions. You build a nice table and you work you out through the process to calculate the pH. Now, I just want to give you an idea here. Now, how is that different if you have 0.15 molar HCl? If that's the case, HCl is completely ionizes in water to give you H plus plus Cl minus. And the 0.15 will give you 0.15. There is no need for unstable here. This is one-way reaction. There is no equilibrium. Actually, there is an equilibrium, but the equilibrium constant is so huge, and therefore the concentration of the H plus will equal to the initial concentration, and therefore the pH of that solution will equal to the minus log 0.15. And if you just calculate this on the calculator, that will give you 0.82. So I want you to compare these two numbers here. So for a strong acid in the same concentration, the pH is almost 1. But if you just change that to a weak acid, the pH is a little bit higher, 2.8. So that's important here to understand. Okay, now the next question, it's asking how to calculate the pH of 0.2 molar solution of methylamine, which is CH3NH2. It's a derivative of ammonia, for which the pKb is 3.44. So this is question 4.6. So in here we have this situation where we have a base which is CH3NH2. Just imagine this is like ammonia, and this base is when you put it in water, it's gonna work as a base. That means it is going to accept a proton from the water. So water in this case is the acid. I want you to compare this with the previous reaction. The water was, in that case, was a base. In this case, it's working as an acid to form this BH plus, which is CH3NH plus NH3 plus OH minus, and that's what is the definition of the base. The base, according to Bronson and Lowry, it is a species that accept the proton to form OH minus. And this is a methylamine. So to simplify this, I'm going to refer to the CH3NH2 with B and the CH3NH3 plus with BH plus, and that will bring this equation. B plus water goes to BH plus OH minus. Of course, this is an equilibrium because of the fact that methylamine is a weak base. Now, how do we know it's a weak base? Well, based on its BKB, it's 3.44. So if you calculate the KB, it will be a small number. Okay, we are provided with the BKB, and we are asking for the pH, and we have an initial concentration of 0.2 molar. The solution for this problem, it's very similar to the solution of the previous problem. It's just the difference here is that we are dealing with KB and not Ka. So first we need to calculate the KB of this base. We know that PKB is equal to minus log KB. Well, in mathematics, Px, P anything, is minus log that thing. So PKB is minus log KB, PKA is minus log LKA, Px is minus log X, and so on. So this one, that means 3.44 is equal to minus log KB. And therefore, log KB should equal to minus 3.44. If you raise this, if you raise both sides to the power of 10, you will find that the KB is equal to 10 power minus 3.44, and that should give you a KB value of 3.6 times 10 to the minus 4. 3.6 times 10 to the minus 4. No units for that. Okay, so we get the KB. Now from this equation here, you can write the KB for this one. You cannot write the Ka because this is a base equation, not an acid equation. So the KB for this just made it zoom out so you can see here. So the KB, which is the equilibrium constant for the base, it's again products divided by the reactants, which is BH plus times concentration of OH minus, they are both aqueous, divided by concentration of B. And we need an ice table for this. So you can just quickly, you have B, you have BH plus, and you have OH minus. Okay. So just quickly here, an ice table. So ice. So the initial concentration was 0.2. So you have 0.2 here. You have 0 at the beginning, 0 at the end. This is minus X and plus X plus X. We are lucky here. This is every 1 to 1 to 1. You might have a problem where you have, let's say, 2 OH minus, and then you say this is plus 2X and so forth. You can practice this later on. But this is 0.2 minus X, and this is X, and this is X. That means your KB value, you take it all as always I said, from this line here, from the equilibrium line. So Kb is equal to x squared divided by 0.2 minus x. Now the question is, now we know the Kb for this. Now we just calculate the Kb. It's 3.6 times 10 to the minus 4. Now can we do our test and see if we can neglect x? Are we lucky? So the test is that how much is the value of the initial divided by Kb? It's equal 0.2 divided by 6.4, is it? 6.4 times 10 to the minus 4. Now, of course, you will find this value to be much bigger than 400 anyway. So we're good. That means we can neglect x. So 0.2 minus x, it's almost equal to 0.2. This is what neglecting x means, okay? So now we substitute this equation. So 6.4 times 10 to the minus 4, it's equal x squared divided by 0.2. And you just do your mathematics, you cross multiply, you take the square root, and you will find x is equal to 8.5 times 10 to the minus 3. You can call this molar or the unit. It's molar actually. And what does that mean? That means this x is now equal to the concentration of OH minus, not the H plus. So this is equal, then the concentration of OH minus is equal x, which is equal 8.3 times 10 to minus 3. So from that you can calculate the POH, which is equal minus log OH minus, which is equal minus log that number, and you will find the POH to be 2.07. And therefore, of course, this does not sound a good value for pH for this base. The pH plus POH is equal 14, and therefore the pH is equal 14 minus 2.07, and you will find the value for this base that makes sense now. pH is equal to 11.93, almost 12. This sounds a reasonable number for methylamine with this concentration. The next thing in our lecture is what we call the extent of protonation and deprotonation. So if you go back to any of our problems here, let's go back to this example. So when we threw the HNO2 in the flask here with the water, we know that HNO2 will dissociate to NO2 minus and H plus, and most of it will remain, but how much H plus, how much of that will be dissociating? Is it 1%, 2%, 3%? How do you do that? So simply the percent of dissociation here, it's defined as the concentration of H plus at equilibrium divided by the initial concentration. Just like that's the fraction, that's the percentage of dissociation. So in this question, estimate the fraction of quinoline molecules protonated in 0.01 molar aqueous solution of quinoline. Okay, so that's self-test 4.14. Let's do that. This question will both test your. So quinoline is a base. It's composed of two benzene rings replacing one of the carbons with nitrogen. So this is you just can consider this part of amine, a group, okay? Just like the methylamine that we talked about. So this base, it's a weak base, it can attract or it can get the H plus from water. So we can call this a whole thing the amine structure B. So the B plus H2O will go to a BH plus OH minus. So the H plus will from water will actually go to the quinoline, and it will attach to the nitrogen here. So you'll find you draw this again, and you will just write NH plus instead of N. So pKb for this is 9.112. It's not provided in the question, but it was provided in the previous question. So we have the pKb, and we have a 0.201 molar of the B of the initial base, and the question is asking for the pH, and is actually is also asking for the percent dissociation, okay, or the fraction of molecules that has been dissociated. So we proceed as previously. First, we calculate the Kb because we need it. So pKb is equal to 9.12, which is equal minus log Kb. From that, you can do that, just the mathematics that you have done in the previous question, and you will have Kb is equal 7.6 times 10 to the minus 10. So that's our Kb. Well, I don't want to go over this ice table again. You have to do the ice table and everything. But after writing the ice table, of course, you will come up to a situation where you have Kb, which is the value is 7.6 times 10 to the minus 10 is equal to the x squared divided by 0.01 minus x. Of course, x in this case, it's equal to the concentration of OH minus. If you are not with me here, just go back to the previous question and see how I solved for the methylamine. It's the same thing. I'm just replacing methylamine here with quinoline. Okay, so the assumption is valid here. We can neglect x because of the fact that the initial concentration is much higher than the Kb. It's actually much higher. So the 0.01 minus x, it's almost equal to 0.01. So from this, you can actually find the value of x to be equal to 2.75 times 10 to the minus 6. So 2.75 times 10 to the minus 6, that's your x, which is equal to the concentration of OH minus. You can calculate the pH of this. POH is equal minus log this number, and you will find it to be 5.56. It's a base, so the pH should be more than 7. So pH is 14 minus that number, and it will be 8.44. But the question is not asking actually about the pH, it's asking about the percent dissociation. Which is equal to the concentration of OH minus, actually it's concentration of OH minus, divided by the initial concentration of the base. We know that the concentration of OH minus is that the x value that we found, which is 2.75 times 10 to the minus 6, divided by the initial concentration, which is 0.01 times 100%. That's how you do these things. And you will find the value, which is equal, if you just divide this by this, it's going to be 0.027%. Or as the books say, it's 1/3600. So it's from 3,600 molecules, it's only one molecule that is dissociating in this space. Now, let's move on to the pH of solutions of salts. Now, away from a weak acid and a weak base and a strong acid and a strong base, imagine that we have a salt, which is composed of a cation and an anion, like NaCl. What do you expect the pH of that if you put it in water? What if we replace NaCl with KCN or NH4Br or any other salt? The salts, the pH of salts actually might be acidic, might be basic, and might be neutral. Now it depends. You can easily know or predict if the pH is acidic, basic, or neutral if you can think about where NaCl is forming. NaCl is a salt that is formed between a strong acid, which is HCl, and a strong base, which is NaOH. In this case, the pH is 7, should be 7, because this is a strong acid, this is a strong base. When you titrate this in the lab, the end point is almost neutral, which is 7. Now the story will be different if you're working with KCN. If you think about where KCN is coming from, actually I have to draw these arrows backwards, so like you think where its mother and father is. KCN, it might be coming from KOH, which is the base, and an acid that contains the Cn minus, probably it's HCN. This is one way, okay? Well, this is a strong base. HCN is a weak acid, so who's winning here? It's a strong base. KOH is strong base, HCN is a weak acid. So when they combine, they form a salt. But when you put this salt in water, you expect the pH to be higher than 7 because of this fact. Moving on to the third example in the slide. The example is NH4Br. Now you want to think about where is it coming from? Should it be coming from an acid and a base? Well, there is NH formed, that means there is ammonia somehow reacting with an acid. So this is your base. Where is the acid? What acid can give you the Br? Minus. It's HBr. HBr is a strong acid. Remember the strong acids are HBr, HCl, HI, H2SO4, HNO3, and HClO4. So HBr is a strong acid. It's one of them. This is a weak base. Ammonia is a weak base. So who's winning here? It's the strong acid. So when you put this in water, the NH4Br, when you put it in water, you're going to form a solution with a pH lower than 7. How much is it? I don't know. It depends on the concentration. It should be 6, 5, 3, 2, whatever. Anything less than 7. It depends on how much of that, what is the concentration of the NH4Br. This is very important to understand at this point here for you to know what buffers are. Okay, so there is a question here that says estimate the pH of 0.01 molar sodium acetate. This is an acid. It's not a weak acid. Sorry, this is a salt. It's not a weak acid. It's not a weak base. It's just a salt. It's a salt that is forming from acetic acid and sodium hydroxide. It's a powder. It looks like a white powder. You throw it in water in the lab. Do you expect the pH to be 7, lower than 7, higher than 7? And how much is it? Let's go over this question. So CH3CONA is a salt that probably it's forming from, well, we have to divide this into two parts. So you have here the anion, which is CH3CO minus, and the Na plus. So who's forming this? I just want to here to expect what is the pH. Well, this might be coming from an acetic acid, which is a weak acid. And the Na should come from a strong base, which is NaOH. So therefore, this is a strong base. I'm expecting this. I'm just expecting this, the pH to be higher than 7. Why? Because this is a strong base, weak acid reaction. Or a strong base, weak acid forming a salt that when the salt goes to water, it's going to form some species with a pH bigger than 7. Let's see if that's true when we work in the mathematics. This is the equation of reacting sodium acetate in water liquid to give CH3CO minus plus Na plus. A salt dissociates completely in water. This is not a weak acid. This is a salt. It's completely soluble in water. If you go back to chemistry 101, you know that acetate ions in the group 1, they're all completely soluble in water. That means when you put them in water, they're going to form you CH3CO minus plus Na plus. This is not a kind of a situation like the weak acid. This is not a two-way arrow. This is a one-way arrow, okay? Because this is a salt, it's soluble in water. When you put it in the water, it's going to form this species and the Na plus species. Now let's take this species, which is the acetate, which is the one we are interested about. The acetate here, when you put it in water, is going to form you CH3COH plus OH minus, but this reaction is actually a reversible reaction. It's in equilibrium now, because just look at the other way here, CH3COH plus OH minus. This is a weak acid forming the, if you go reverse, it will be a reversible reaction, then the whole thing is reversible. Okay, I'm just going to simplify this with equation, just to simplify things. It's going to be A minus plus H2 liquid goes to HA plus OH minus, and A minus here is the base, which is the conjugate base of the salt. So what else we have information here in the question? Do we have any? Okay, we have an initial concentration which is 0.01. So if the concentration is 0.01 of the salt, and the salt is completely soluble in water, that means we have also 0.01 of this, and we have 0.01 of this. And that means we have 0.01 of this, of the A minus. But in this case, the concentration of the OH minus and the HA is not equal to that number, because you need an ice table here. This is not a one-way reaction, this is a two-way reaction. So let's make an ice table and see how this works. So an ice table, that means you have to do initially and change and equilibrium. So initially you have 0.01 of the A minus from the salt, you have 0 of this, you have 0 of that, you have minus X for the change, you have plus X for this, plus X for that, and you have here equilibrium, that means 0.01 minus X, and this is plus, and this is X, and this is X. Now, this is a base, it's not an acid. This one is a base, so you cannot actually apply the Ka for that. So this is a base, you can apply the equation, which is Kb for the acetate ion. It's equal to x squared divided by 0.01 minus x. But what is Kb for the A minus? I'm not provided with that. I am provided with the Ka of acetic acid. The Ka for CH3 COOH, it's equal to the 1.8 times 10 to the minus 5. This is a value that I'm providing for you. How do you calculate that? Well, we know that Ka times Kb is equal Kw. That means Ka times Kb is always equal to 1.0 times 10 to the minus 14. This is a rule that the products of Ka and Kb. So you can calculate actually Ka from Kb and vice versa. And this is good. Now we know the Ka is this number, so we can calculate Kb. So Kb, in this case, is equal to 1.0 times 10 to the minus 14, which is the Kw for water, divided by this number, which is 1.8 times 10 to the minus 5. And now we have a Kb value equal to 5.56 times 10 to the minus 10. Of course, you can do your assumption here again, and you divide the initial concentration divided by the Kb, and you will find it to be more than 400, so we're fine. So, and you work your math. I'm not going to do it again here just for the time saving, because I am assuming that you know now. And you will find x for this case to be 2.36 times 10 to the minus 6. 2.36 times 10 to the minus 6. That's your x value when you solve the question after that. Of course, this is equal to the concentration of what? Let's see what does x mean here. When you back to this equation, it's A minus plus H2O goes to HA plus OH minus. The x is actually it's concentration of OH minus, not H plus. So this is equal to the concentration of OH minus, and therefore the pOH of that, you can just minus log that, and you will have 5.63 is the, and the pH is, yes, as I expected, it's actually more than 7. pH is 8.37. 8.37. Did we say pH is higher? I forget. We said pH is higher than 7. Okay, pH is higher than, it's almost 8 point something. Okay, so this is how you solve problems for the salts. In the next lecture, we're going to talk about polyprotic acids, and also we're going to talk about buffers. So thank you so much for listening, and have a great day.